afternoon. This is Schweitzer, and we're going to run through a little video here on elementary reactions. This is just some skills that we're going to use quite often. Alright, so first things first, chemical reactions at a molecular view. Typically we have reactions that are either unimolecular, bimolecular, or termomolecular. Now what does that mean? So unimolecular means that there is only one reactant. An example of this would be like just X going to Y. Alright, that's pretty common. Bimolecular would be there's two reactants. Okay, and that'd be like X, could be X plus X reacting to produce Y. Okay, or X plus Y, doesn't matter. So in order for this reaction to occur, we literally need two X's to physically collide at one instance in a certain way with certain energy to get Y. This one is completely just on its own, so just could be breaking down. So in this case, termomolecular would be one where there's more than two. More than two. This starts to become really problematic. We have X plus Y plus Z produces, let's say, smiley face even. Okay? So with that being said, I literally need all three of these to collide at the same time in the correct fashion with the correct energies. That ends up being really difficult. Sometimes I make the analogy of three people. If you blindfold them and walk them and they have to wander around the mall, what are chances that all three of you physically bump into each other at the same time? Almost impossible. So it's theorized that reactions actually take part in multiple steps. We call these elementary steps. Where maybe two things, X and Y, could react to form some sort of intermediate, XY you might call it, and then XY could react with Z to produce the new substance. We call these elementary steps, and that's what we're going to kind of talk about today. I would imagine that these things are really happening on a molecular level, and they're basically often thought of as being theory. It's really difficult to know exactly what happens. We call this an intermediate. It never shows up in the end. It is produced and consumed within the process. Very short life. Can't really detect it. So it's a theoretical option. Okay. Alright, so here we go. So reactions have orders. What does this mean? Okay, so we'll talk about this again in other places, but zero order essentially means that concentrations of reactants have no effect on rate. There are lots of examples of this. I would say, for example, alcohol and digestion by your liver. It only digests so fast. You drink lots of alcohol, it digests at a certain rate. You have a high alcohol content in your body, it's a certain rate. It doesn't start faster and then slow down. It just goes at a certain rate. First order would be something that is proportional. So if I double my concentration, then I would also be doubling my rate. Whatever I do to my concentration, I would be doing to my rate. That would be something where if I doubled the amount of alcohol I drink, I would double the rate which it digests. This is not the case, but there are lots of things like this. This is another example where we have a situation where we have, if you were to, it's squaring essentially. So if I double my concentration, I would be multiplying my rate by 4. Or if I were to triple my concentration, I would be increasing my rate by 9. So what is a rate law equation? So the rate law equations are going to be, this is one of our main ideas or main things we're going to do. The whole purpose of science is to create models that predict the future. And the rate law equation is one of our main models. It is designed to calculate the initial rate. It only says rate on here, but it's important to realize that this is the initial rate. So that's the rate at the beginning. How much at the beginning? It doesn't really say. It's just like the beginning. Pour two chemicals together, mix them up, and it's running, like kind of right there. To find the rate at an alternate time is much more difficult. So the rate, initial rate equals, okay, now we're going to have a equalizing constant we call K. And then if I have a reaction that's just X going to Y, then this guy is going to be just times the concentration of X. And then this is the number of actual items is the order. So if by chance it's 0 order, that's my orders. 0 would mean something that is not affecting the actual rate. Okay? So for whatever reason, this concentration is not affecting the rate, so it goes 0 there. Again, this is just a model with predictive power. If I were to plug a number in here for the rate constant, we call this the rate constant, then no matter what I put in for the concentration, it's just going to stay the same. I could double this to 0 power is 1, so it just stays the same. And that point, just so you know, my rate would equal K, whatever my rate constant is. So what if I have a first order? That would be rate equals K times the concentration of X. Let's say now X here would be to the first. Okay. This is typical of something where there is one molecular, one thing. This is the number of items, the number of like individual items in the reaction. And we'll talk more about this as we go. So this could be something that simply X goes to Y. Again, like that one. Okay. All right. Single step reaction. Again, not multiple steps, but single step. One step reaction, X goes to Y. Okay. All right. Another example, second order. So that means for second order, I need two things bumping into each other. So it'd be X plus X yields Y. So I have two things here. So it's going to be rate equals K, and then the concentration of X to the second power. This is going to be meaning that if I have a square here, then I double this, then the square goes to 4, that means that this guy gets multiplied times 4. So these are common, very simple rate law examples. We have a first order, second order, and 0 order. So these are models that our first quiz is all about, coming up with these models and doing things differently. But ultimately it's about either calculating the initial rate, or if you have a rate, what concentration would be required to hit that rate. All right, so let's see an example of this. This is just what we just talked about. Okay, doubling the concentration of A will double the reaction rate. That means here, typically one single step reaction would be there's one item present, and they may not put a 1 there, but it's there. Make sure you have this idea that this will be a single step reaction, therefore it would be first order because there's one item there. In this case, all right, A plus B. Remember, these orders are the number of items present in the what's called the rate determining step, but this is the only one step reaction. So I used to use the word rate determining step. That's something that's new, and we'll be talking about it more later. But one step reaction, not elementary steps, one step, so A and B must collide. There's 1A, there's 1A. 1B, 1B. It's first order with respect to A. It's first order with respect to B. Okay? But the overall reaction, to get the overall order, this is important here, the overall order is 2. How did I get that? 1 plus 1. Add up these guys here to give you the overall order of 2. And that's just a kind of question they ask a little bit about. Doubling the concentration of each will quadruple the rate. Doubling this doubles that. Double this doubles that. Double both of them, quadruple. And of course, you could always just plug in a random K value and try it out. Alright, how do we know a reaction happens in multiple steps? As I mentioned earlier, it's nearly impossible for a reaction to have 3 reactants and run in a single step. All 3 would need to come together at one time. You could have it work, but you'd need to have really high concentrations, and it would take a long time. So we propose that reaction run multiple steps, producing intermediates that get consumed inside of a reaction. Okay, so this is important things that we need to understand why it's probably likely that things run in multiple steps and how we theorize that this happens. We never know anything for sure. Alright, so here's a proposed set of elementary steps. Now, this is just some general stuff that we use all the time. So how do we go about coming up with an overall reaction? Now, there's a couple of ways you can do this. One, take all the stuff you have here and put it over here. I have 2 A's, I got a C, I have a G, and I have an E. What do I have on this side? Okay, I got a B, I got a C, I got a D, I have an E, I have 2 F's, and I have a G. Anything that's on the same both sides, you can just cross off. There we go. And looks like we got, what else we got here? We have an E, C. So my overall reaction at this point should be 2 A's plus, looks like there's nothing else there, 2 A's produce a B and a D and 2 F's. That's one way to come up with the overall reaction. The other way, I would start this way, but the shortcut way would just be to cross things off that are on both sides. I have a C here, C there. I have a G here, G here. I have an E here, I have an E here. And then at that point, I would just simply add everything up. I have 2 A's. I am producing a B, a D, and 2 F's. B, a D, and 2 F's. Okay. All right, so common questions here. What's a catalyst? A catalyst is the same as a normal reactant, like A is a reactant. I literally have a beaker, and I just drop A in. Okay? But I also got to drop in the catalyst if I have to drop in a catalyst. All right, so what do we got here? Well, what's a catalyst? A catalyst could be something I add. I physically have to add it. Okay, so did I have anything I added? So it comes in here and gets kicked out. This was produced and then got consumed. This is an intermediate. Okay. All right. B was produced and it was stayed. All right. A is brought in, and it's right there. Okay. D is produced as a product. E is produced and then consumed. But G here, look at G. G's added in here, but it's not in a reactant, and it gets brought in and then kicked out right here. That's a little bit different. C is intermediate. G is a catalyst. And I could put G right here if I wanted to. So catalyst would be G. Intermediate would be C. Important to see the difference. It's produced and consumed. You didn't physically add C. And C would be somewhat theoretical. We don't know for sure. We're hypothesizing about C. All right. And I think that's my only intermediate. E is intermediate, produced and consumed. So C and E are considered intermediates. If I'm doing a rate law for this thing, I can only include things in my rate law that are actual reactants. So I would do rate law, rate equals my K value, and I got to use all my reactants and my catalyst. So it's going to be concentration of A, concentration of B, G. That's my catalyst. And that's something I physically add. I don't know my orders yet. We'll be talking more about that later. But this is what we can do for our rate law so far. You cannot use an intermediate in your rate law. Okay. All right. moving along here. Okay. Energy diagram. Again, I'm going to pause on that for a minute. We'll skip this for now. Okay, we did this in the last video, so I'm going to move that around a little bit. All right. Well, actually, let's just run a quick review here. The energy diagram. Energy diagrams start with exothermic. Just run like this. And in this case, the exothermic reaction is exothermic. Okay. So it goes from, this is my delta H, and this is my energy of activation. From here to here, start to peak. Okay, so that's this guy located right here, peak to here. All right, what about endothermic reaction? That starts low and ends up with a higher energy. And this guy here, all right, what we got? From start to end is my general energy here. Okay, this is my delta H, change in energy. From start to peak, grab a different color here. From start to peak, that's my energy of activation. So endothermic reactions have big energies of activations. Okay. All right, what does an energy diagram look like for a multiple step reaction? Okay, so now when you have a multiple step reaction, in this case, 2 steps mean we have 2 bumps. Okay, now I'm going to go endothermic here, exothermic here. There could be multiple ways we do this, and I don't know how big the energies are. So, and this means energy in is endothermic, so I want to start low and end high for my first bump. That's endothermic. Next one's exothermic. So again, I don't know how high it goes, but I do know that it ends like this. Okay. My overall reaction is exothermic, and I do have a slight exothermicness here. It's dropping. Okay. So what do we want to get out of this? Each step has got a bump. Okay. And we'll bring this on later, is that one of the bumps will be bigger than the other one. So if this one here, let's say that this energy is the biggest one, then this might be a little higher, and this is called our rate determining step. So we're usually looking, and you'll find more about this later, just a little hint for the future, rate determining step. Okay, so again, this is just energy, and this is time. Just ran this through in the previous slide. So that was a little reminder on the previous slide of how this works. Okay, so big important things there. All right, look at this guy. First of all, how many elementary steps are there? There are 3 elementary steps. Step 1, step 2, and step 3. So 1, 2, and 3. Which one's the rate determining step? That's going to be step 2. This is going to be the one that is the biggest hill to get over. Biggest energy needed. You can get over 1 just fine. Get over 3 just fine. But if you can't get over 2, it's not going to happen. So this is the one that really controls everything as far as the rate of the reaction. All right. Take a moment. Pause the video. Try it. Rate the reaction, identify intermediates, identify any catalysts. Okay, first things first, I'm going to go with my normal fast way of doing things. So A, cancel things out, so G is canceled out here, and everything else looks pretty good. So I'm going to have A plus B plus C yields D plus E. All right, in this case, there was anything introduced, A, B, or C, that was kicked out then? And the answer is no. So there is no catalyst, none. And intermediate would be G. Important skill there. All right, we're ending our reactions in elementary steps, and next we're looking at generating the rate law from the elementary steps, and we'll be using rate determining steps for this. Thank you very much.